In this episode, we're going to talk about the concept, the very important concept, efficiency, which is also known as Pareto efficiency. So here is the informal but intuitive definition of Pareto efficiency. An allocation is called Pareto efficient if it is impossible to make one person better off without making another person worse off. So this is another way of saying improvement is impossible. Well, I will later make this more concrete, more formal in the context of pure exchange economy. But what I would like to underline so that we can understand what this statement really is that this statement, this concept can be applied to almost any environment. However, we need to be clear about few things. One of them is what is allocation. So you have to have a well-defined structure so that we know what allocation is. Well, the second important thing is, well, obviously we need at least two person, right? Because here, as you see in this definition, it says it is impossible to make one person better off without making another person worse off. So basically, one guy is sort of well-being is improved, but then the other guy's welfare will be decreased. All right, so therefore we have to have an environment where there's at least two individuals. More than two individuals is perfectly fine. All right, so the third important thing is, well, what do we mean by being better off and worse off, right? So let me underline the allocation. We have to be clear about it. And then one person versus another person. All right, so we need at least two people. And then what do we mean by better off, worse off? Well, here in the context of microeconomic theory, obviously, we are talking about preferences, right? So, or utilities of individuals. So therefore, better off basically means the consumer's utility is increasing or the consumer or the person is getting something he or she prefers more. And being worse off means the consumer's or the person's utility is decreasing and or she's getting something worse than, in terms of her preference ranking, something worse. So here, if you sort of think about this, the idea of better off, worse off is actually a consequence of making comparison, right? So what we are doing basically, we have two individuals. Let me denote them as such. So these two individuals are initially given some allocation, whatever that allocation is. So that depends on the context. And then, well, if we are talking about being better off, right, it's relative. Better off with respect to what? So in comparison to this allocation, we should be comparing again the same two individuals, meaning their preferences are not changing, right? So the preferences are fixed. Preferences or the individuals are the same. I'm just comparing two different scenarios. All right. So in one scenario, I give them an allocation, and here I give them another allocation. Again, whatever allocation means. Let's leave this vague for now. So then I'm basically comparing how happy these two guys will be. Or by the way, maybe there are more than two guys. All right, so at least two guys. So I need to sort of here see how happy these individuals are. And then I need to see how happy these individuals are in this second scenario under another allocation. And so compare these two welfare levels or sort of well-being levels or the utility levels, right? So if one agent is getting better off, all right, think of this as like one agent is getting more goods. So allocation is, let's say, consumption good. So agent one is getting more good. And then that means, so if this allocation is efficient, that means the second agent is basically getting less good then. right? I mean, very intuitively, you can think it this way. So here, one very simple framework and example. So let's suppose these two guys found $100 bill while they were walking on the street. All right, so $100 bill. Well, the thing is, they would like to split this bill because, you know, that seems like the fair thing, because one guy owning everything and then the other guy owning nothing doesn't seem fair to these guys. And so they would like to split this. Well, the question is, how are they going to split the $100? Well, obviously, so let's suppose any division is possible, all right? Meaning they can divide it 50-50, they can divide it 80-10, 80-20. So all they have to do, they just have to go to some, you know, grocery store, ask the cashier, do you have, you know, $100 or, you know, $10 bills or $5 bills, you know, some change, and so that we can easily divide this $100 among us. Well, the question is, let's say something about the preferences. So let's suppose these people, these two guys, are actually preferring to have more money than less money. All right, so the more money brings a higher utility than less money. Okay? So everybody prefers more money. So here, then, what is an allocation? All right, so here, an allocation is basically how these guys are going to split the $100. So you can think of the general way, one specific example, 50-50, right? So this is one allocation. That means, you know, each receives exactly the same amount of money. Another allocation, that's not the only allocation, obviously. Another allocation is 80-20. Like the first guy is getting, you know, let's say the first guy is, you know, Bob, and then the second guy is Anita. So Bob gets $80, Anita gets $20. Or obviously 20-80 is also an allocation, right? Well, this time Bob gets the smaller portion. Well, why 80? I mean, what is special about it? Well, obviously nothing special about it. You can think of 60-40, 55-45. All right, so basically, any x, 100 minus x, where x is somewhere in between 0 and 100, is basically an allocation. Agree? All right, so clearly allocations like 100-0 or 0-100, meaning one guy gets everything, the other guy gets nothing, is so unfair, right? Well, whatever fair means, we don't really define it, at least in this context or in economics. I mean, in pure exchange economy. So this seems like a very, very unfair. But once again, we're not defining fairness here. We're talking about efficiency. So what does it say? Well, then efficiency basically means an allocation is efficient. It is impossible to make one person better off without making another person worse off. Well, here, obviously, you can argue whether it is an allocation or not, right? You can think of something like this. And sort of a one potential division of $100. So Bob gets $30, and then Anita gets $30, all right? So the question is, so it's not one of those allocations, right? So, but nevertheless, this is one way of dividing $100 between these two agents, but you're going to sort of object, well, here the sum is $60. What happened? So they had $100, so what happened to this additional $40? So let's suppose they pay this $40 to some a homeless guy that they saw on the street, all right? Well, the question is, do they get any utility out of giving money to this homeless guy? So that's very, very important. So let's suppose, so here we did not specify that. All we said is the more money brings higher utility than less money, all right? And let's suppose giving out others, you know, giving money to others doesn't give additional utility, right? I mean, I need to know these guys' preferences so that I can judge whether this allocation, this division of $100 is efficient or not. So here, therefore, again, giving out something, for many people actually, giving money to other people could actually bring some joys. So here, for simplicity, let's suppose it doesn't. All right, so both Bob and Anita would actually prefer to have the entire $100 to themselves. All right, so that means, splitting this $100 as 30-30 and giving away some part of it is clearly inefficient. All right, so this allocation is inefficient, or this way of splitting $100 is inefficient. Why? Well, because, so this is basically the initial allocation, right? 30-30. Is it efficient? Well, the answer is no. Why? Well, because there actually is another allocation, meaning another split of the $100, for example, 50-50, where both Anita and Bob gets higher sort of amount of money. And therefore, according to their preferences, they both will prefer this allocation over, that's the key thing, they both prefer this allocation over this allocation. So it is possible to make one person better off without making another person worse off here. So that means, therefore, this allocation for these two guys is inefficient. Well, what is special about 30-30? Nothing is special about 30-30. With the same reasoning, if they split it something like 60-30, for example, that's also inefficient. All right? What does that mean? That means they are splitting, well, yes, Bob is getting more than Anita, but the thing is, they're still wasting, all right? So according to their preferences, they're wasting $10, all right? And this additional $10 doesn't bring any one of those guys any utility. So how do I know that this is an inefficient allocation? Well, this time the question is 60-30 efficient? Well, the answer is going to be no. Why? Well, because there's another allocation. I need to show that there's another allocation where, for example, they split 65-35. All right, so this additional $10 that they're wasting, they're basically sharing it half and half. So 65-35 brings joy to both Anita and Bob. And so, therefore, it is possible to make one person better off without making other person worse off. And hence, this is also inefficient allocation. All right? So these are inefficient. Well, what about these guys? Well, all of those, meaning whenever, Bob's share plus Anita's share add up to 100, exactly 100, well, then that allocation is efficient. And here, there are infinitely many efficient allocations. All right? Well, I know it is highly unfair, but 100-0 is efficient. Agree? Well, why so? Well, because if you want to make one guy happier, well, here, there's no way you can make Bob happier because he is already receiving everything. So here, you can only make Anita happier. So the question is, when you make Anita happier, are you going to make Bob worse off? Well, obviously, because making Anita happier means you have to give Anita more money, more than zero. All right. And so that means, well, where's this money is going to be coming? Well, don't forget here, the entire world outside of this sharing $100 is like empty. All right. So you cannot bring extra money into this picture. So forget about what's happening outside of the world. Let's just focus on this. Let's split $100 problem. All right. So in reality, for example, I know things are like different. For example, Anita may say, look, give me, $50 because currently you're giving me nothing, but give me $50. You know what? I am going to, for example, cook dinner for tonight. All right. So basically you are bringing extra stuff. So you are changing the concept of allocation. All right, so you have to be careful. The concept of allocation in this problem is how much, what percentage of $100 is Bob going to get, and what percentage of $100 is Anita going to get. All right, there's nothing else. So be careful about it. So once it's fixed, if you want to make Anita happier, well, you have to take some money from Bob and give it to Anita. Well, that will obviously, so what does that mean? That means, for example, you're going to subtract some money, let's call it, Y amount of money, and then give it to Anita. Well, yes, Anita is going to be happier as long as this Y is positive number, but clearly because more money is giving more utility to these guys, Bob is going to get worse off. So what does that mean? That means once you are thinking of this allocation, all right, 100, 0, is this Pareto efficient? Well, the answer is yes, it is Pareto efficient, because whatever another allocation you propose, well, clearly it is impossible to make one person better off without making another person worse off. So somebody will get worse off. So therefore, this allocation is efficient. All right. So improvement is not possible. So joint improvement is not possible. That's very, very important. So once again, so it is very unfair, but it is efficient. There's nothing special about 100, 0. Another scenario where Bob gets 0, Anita gets $100 is also efficient. 50-50 is also efficient. 80-20 is also. So as long as their share sum up to 100, it's going to be efficient. Obviously, their share can never sum up to more than 100 because they don't have more than $100. They have exactly $100. And so in this very simple framework, any allocation where the sum of the shares add up to strictly less than 100 is going to be inefficient. All right. So this is it for this very simple framework. Well, the question is, what about in a pure exchange economy? So here, the nice thing about this example is that if you want to make one guy happier, so you need to give more money, you have to subtract. So this is why I put this minus here. You have to subtract the money from the other guy. So it seems like a lot of things are efficient, right? So efficiency is not really bringing me, something tangible in this framework. But the thing is, when it happens to be in a pure exchange economy where there are at least two goods, so there's good 1 and good 2, and so what is the allocation? Remember, allocation is how much Bob and how much good 1 and good 2 Bob is going to consume, and how much good 1 and good 2 Anita is going to consume. By the way, we can generalize this to M many goods. So 2 is just for simplification. Well, here you do not, when you sort of compare one allocation with another one, you don't have to compare like you give more in both good 1 and good 2, and therefore subtract from the other guy for both good 1 and good 2. So you don't really have to worry about this type of scenario. Well, what you have to worry about is, what is sort of interesting in this framework, in the pure exchange framework with more than two goods, is that the rate of substitution plays an important role, right? So think of this like, Bob loves, for example, apples, and Anita loves bananas. And so they have to share apples and bananas, all right? So think of this as like, yes, they found $100, but then, somebody needs to cook dinner, all right? And so there are, two goods. Who's going to cook the dinner? And then how we're going to share the money, all right? So when there are two goods or more than two goods, well, then the marginal rate of substitution is going to play an important role. So maybe, yes, both guy enjoys more money, but the thing is maybe Bob hates cooking dinner and Anita actually enjoys it. And so you see what I mean? So they can actually use this rate of substitution in order to make efficient trade. And so improvements can actually be possible. And so we may not have everything well, I mean, here, these are not everything, but I mean, almost everything is efficient. So we may not have conclusions like everything is efficient. All right. So, or, the set of efficient allocations may have sort of a more refined properties. So let's consider one example. Now let's consider this example. Well, now I give you the utility functions, so that we know how Anita and Bob are going to compare the bundles, the allocations. So these are sort of the preferences of these two guys. So here, an allocation, therefore, remember, is how much good 1 and good 2 Anita is going to consume, all right? And obviously, and how much Bob is going to consume, good 1 and good 2, Bob is going to consume. So this is what allocation is. So this is also represented as Anita's bundle or consumption and Bob's consumption, all right? Well, here, what we need is the boundaries of this problem, right? Meaning, for example, the question is allocation XA, XB, which is equal to, for example, 2, 2, comma, 1, 1, efficient? All right, good question. Is this efficient? Well, remember the definition of efficiency. It's impossible to make one person better off without making another person worse off. So, there's one initial situation and then another bundle. Can I find another allocation where they both actually get happier? Is it possible? Well, obviously it is possible. For example, if you compare this allocation with this allocation, 100, 100, all right, 100, 100. So clearly this allocation is going to bring both of these guys higher, much higher utility. So therefore it is possible to make both agents happier. But hey, there's one problem here. Question is this efficient? Is this feasible? I mean, remember the splitting $100 example? So here, there's good 1 and good 2, but are they limitless? The amount of good 1 and amount of good 2 in this economy, what is it? If it is limitless, well, you know what? There's almost nothing efficient because improvement is always possible. But we know in reality things have limit. So therefore, this was the idea of initial endowment, right? So when we defined pure exchange economy, we said, well, there's no production. Everybody brings some good 1 and some good 2 to this market, and then they exchange. So let's suppose W1A and well, yeah, I'm going to say W1. So the total endowment for good 1 is equal to 3, and total good 2 is 3. So in this economy, there are 3 good 1 and 3 good 2. All right. So therefore, this is, for example, feasible, and this is infeasible. All right. I mean, this allocation is out of question. So you can't say it is possible to make both agents happier because, well, I mean, this is not possible. All right. So we eliminated this by basically putting some limit on how much good 1 and good 2 is available. Well, the question is this efficient? That question still remains. Well, obviously, I cannot give more of good 1 and good 2 to agent 2 and make agent 2 is Bob, agent 1 Anita happy. Make agent Bob happier and without hurting Anita, right? So because if I want to give more of good 1 and good 2 to Bob, well, that means I have to subtract some good 1 and some good 2 from Anita. So therefore, this is not the way to improve their situation. But that doesn't mean that improvement is impossible. It is actually possible. How so? Well, look at the marginal rate of substitution. So here, Anita cares about or gets utility, 2 times more utility on good 1 than good 2. So she values good 1 much more, 2 times more than good 2. And for Bob, the opposite is true. Kind of, well, it's 1 to 3, but the absolute values here is irrelevant. What matters is that he is actually caring about good 2 rather than good 1. So you know what? Instead of giving 2, 2, 1, 1 to these guys, let's give them, for example, give everything to, all the goods to Anita because she's the one that cares about good 1 the most, and give everything, all the good to Bob. Can this be an improvement with respect to this one? Well, I don't know. Let's see. Let's compare. How do I make this comparison? Well, first of all, let's write this allocation where Anita gets all the good 1. Well, we know that there are 3 good 1. And so Anita gets 3 good 1, 0 good 2. And Bob gets 0 good 1, but 3 good 2. All right, so therefore, this is the allocation. The question is, in comparison to this, are they, both Bob and Anita, getting happier, better off if they consume this bundle rather than this? Well, you have to compare the utilities, right? So what is Anita's utility here? Given that, don't forget, she's consuming 2 and 2. Well, her utility is 2 times 2, 4, plus 2, 6. Well, here, what is Bob's utility? 1, 1. It's 1 plus 3, so 4. Good. Well, what about here? The Anita's utility of consuming 3 good 1 and 0 good 2 is, 2 times 3 plus 0, it's 6. What about Bob's utility of 0, 3? Well, it's 0 plus 9. So, what happened? Well, Anita is indifferent because for her, her utility level when she consumes 2 good 1 and 2 good 2 is exactly the same as consuming 3 good 1 and 0 good 2. So she's indifferent. However, Bob is happier, strictly. So let's go back to the definition. It says an allocation is Pareto efficient if it is impossible to make one person better off without making other person worse off. However, here, it is possible, I just show, that it is possible to make one person, which is Bob in this scenario, better off without making Anita worse off. Anita is indifferent, so she's not worse off. But I actually made Bob happier. So it is possible. So what does that mean? Well, then that means this allocation is not efficient. All right? So therefore, this is inefficient. Sometimes we ignore Pareto part, so we don't say Pareto efficient all the time. We just call it efficient or inefficient. All right, so therefore this is an inefficient bundle allocation. For us, it's the same thing. All right. So here, be careful. It's like there might be infinitely many other options where both Anita and Bob happier, but I don't care. All I want to find is that there may exist another feasible bundle where, both guys can be happier, or at least one guy gets strictly happier and then the other guy remains to be indifferent. All right. So if I can't find such allocation, well, then I can say that the allocation that I'm checking whether it's efficient or not is in fact not efficient. All right. So once again, there might be infinitely many such bundles which are better than this one for both agents. But I don't care. All I need to do is just to find one such bundle or allocation. Well, the question is, showing that something is efficient is actually very difficult, as you see, because you have to show that you can never find such a bundle, all right? Never, ever. So let's try to come up with some allocation which is in fact efficient. An example. So, well, let's pick this one. Is this efficient? 3003. Well, so again, this is hard to check in general. But here in this example, the question you should ask yourself is that when Anita is consuming 3 good 1 and 0 good 2, can I make her happier? All right. Well, if you want to make her happier, all right, what you have to do is you have to give her more x1 or more x2. Well, you cannot give her more x1 because she's already consuming all the x1s. All right. Well, then that means this is off the picture. I can give her more x2. But the thing is, so some epsilon x2. So if I give her some epsilon x2, well, by the way, if epsilon is 0, right, that means Anita is going to be the indifferent with consuming 3, 0, because I couldn't really change her situation or allocation. And then, but remember, this is a feasible allocation, meaning, I'm sorry, this is a feasible allocation. So meaning they are already consuming all the good 1 and good 2 available in this market. All right. So therefore, I cannot bring additional good 1 or good 2 from outside of this market. So then if I want to make somebody happier, let's say it is Anita, I have to give her higher good 2. Well, what does that mean? That means I have to give, or sort of subtract some good 2 from Bob, because otherwise right? So the total of 3 good 2 is already consumed. So if I'm giving additional good 2 to Anita, well, those good 2s are going to be coming from Bob. Well, so here, this minus epsilon guy is like, look, I tell Bob I'm going to reduce his consumption on good 2 some epsilon amount. And then obviously that's going to hurt Bob. So that means that I can't really find the improvement. So if I am looking for an improvement, and if I am subtracting some good 2 from Bob, well, then that means I have to give Bob some additional good 1. All right. So plus of, I don't know, delta. All right. Positive. So, right. I mean, I have to compensate him. But the problem here is there's a 3-to-1 ratio. This marginal rate of substitution plays a very important role. So with this additional change, so what I have is the following. So before, the Bob's consumption is x1 and x2. So these are Bob, let's suppose. So I am ignoring the superscripts. But before, the Bob is consuming x1 and x2, and therefore the utility x1 plus 3x2. And after, well, Bob is consuming x1 plus delta, right? And x2 minus epsilon. So what is the utility out of this bundle, this consumption bundle? Well, it's x1 plus delta plus 3x2 minus 3 epsilon. So therefore, before and after comparison, net change in utility is what? Well, the net change is x1 plus 3x2 minus x1 plus delta plus 3x2 minus 3 epsilon. So if you make this subtraction, you'll see that this is equal to 3 epsilon minus delta. All right. So the next exchange, net change in utility is basically before and after. So if I am looking for improvement, all right, well, this has to be less than 0, so that after is, right, the payoffs, I'm sorry, utility after the exchange is greater than or equal to utility before the exchange. So it has to be, this difference has to be less than or equal to 0. So this has to be less than or equal to 0. So what does that mean? That means delta has to be greater than or equal to 3 epsilon. All right? So if I am giving, so once again, the idea is coming from here. If I want to make Anita happier, I have to give her some epsilon amount of good 2. I can't give her some x1 because she's already consuming all x1. So from this, I said, well, if this epsilon is given to Anita, well, that epsilon should be subtracted from Bob. And well, if I don't give Bob additional x1, obviously he will get worse off. And so there's no way that can be an improvement, Pareto improvement. So I have to give him some amount of x1 so that he's indifferent between before exchange and after exchange. So that I can say, well, Bob's utility is remained the same, but Anita's utility is actually improved. All right. So therefore, what I have shown is that in order to have improvement, or maybe Bob is indifferent, well, this difference has to be less than or equal to 0, which basically implies that this delta thing has to be 3 times more than the epsilon thing. All right, but what about Anita? So it's the same thing. So before, the Anita is consuming x1, x2. But don't forget, these are A's, and so I'm ignoring the A's here. And her utility is 2x1 plus x2. So after the exchange, what we have is the following. So now, don't forget, this delta is given to Bob, but it has to be subtracted from Anita, right? I mean, otherwise, where is this additional x1 is coming from? Out of nowhere? No, it has to come from Anita, because Anita is the guy who is consuming all the x1s. So therefore, after the consumption bundle for Anita is the following: x1 minus delta and x2 plus epsilon. And her utility in this case, let me write it here, is 2x1 plus x2, which means 2x1 minus 2 delta plus x2 plus epsilon. All right? So if you look at the net change in utility, again, before minus after, which if we want to talk about this after exchange, there's an improvement, it has to be less than or equal to 0, same as in this case. So before is 2x1 plus x2 minus after is 2x1 minus 2 delta plus x2 plus epsilon, less than or equal to 0. If you do this subtraction, these will cancel out, x2 will cancel out, so this minus and this is going to make it positive. Therefore, I have 2 delta minus epsilon less than or equal to 0. I must have epsilon greater or equal to 2 delta. All right, so what I'm basically showing here is the following. So given that Anita and Bob is consuming or sort of planning to consume this bundle, my question is improvement possible? Well, the improvement is possible if basically I subtract some good 1 from Bob, give it to Anita, and extract some good 2 from Anita and give it to Bob. And well, this subtraction and givings, meaning this epsilon and delta, must satisfy these two inequalities so that they can actually improve in comparison to this. All right. So remember, we are always comparing when we check whether an allocation is efficient or not. Is like, so this is Bob and Anita, 2 scenarios. So the first scenario is basically this 3, 0 and 0, 3. And then the second scenario is the following, 3 minus delta epsilon, and then delta 3 minus epsilon. Okay, so the question is, I don't know what epsilon and delta should be so that there's an improvement for both Anita and Bob, but what I know is that they must satisfy these two properties. Let's have a closer look at these two inequalities, all right? So, what do they imply? Well, they imply the following. 2 delta is less than or equal to epsilon. all right? And then 3 epsilon is less than or equal to delta. So what I would like to do is like, here I have 2 delta, delta, 3 epsilon, epsilon. So try to make them comparable in some way. How so? For example, multiply both sides by 2. So basically this is equivalent to 6 epsilon less than or equal to 2 delta. Agree? So what does that mean? So the second one and the first inequality basically implies the following. Remember 2 delta is less than epsilon, but 2 delta is greater than or equal to 6 epsilon. So which means 6 epsilon is less than or equal to epsilon. So I know that epsilon can be 0, obviously, but if epsilon is 0, remember I said improvement is impossible. So therefore I have to look at cases where epsilon is positive. But the question is it ever possible that 6 times some positive number is less than or equal to itself? Well, clearly this is not possible because when epsilon is positive, I actually cancel them out. That means 6 is less than or equal to 1. Well, hell no. I mean, I know that 6 is not equal to 1. So this is correct. Therefore, this is incorrect. Therefore, these 2 inequalities can never hold. Therefore, an improvement as such, or any improvement, so improvement is impossible. What does that mean? That means it is impossible to make one person better off without making another person worse off. So given that this is the allocation, it's impossible to improve both Anita and Bob's payoff utilities. So that means this allocation is in fact efficient. All right? Good. Well, I just shown one point as being Pareto efficient. Well, bad news, there are actually infinitely many allocations in this problem that are efficient. So the question is, well, I mean, if only finding one of them costs me, I don't know, 5 or 10 minutes, does that mean that I need infinite amount of time to basically figure out all the Pareto optimal allocations? Well, not really. There's an easier way to find Pareto optimal allocations. And this is what we're going to learn next.